Well, hello friends. Today I thought I would give a little overview of what happens when Serenity boots and sort of go through step by step the boot process and how the kernel starts up and sort of what happens initially until we get to the GUI, because it's something that a lot of people have requested that I talk about, and it's something that it's probably I always like to think that the system is very approachable and understandable, but it's probably much easier to follow along if I just get you started. So this one is for all of you curious people who reached out to ask about this. So I don't have a plan, so so I never make plans. So we'll just boot up once just to see what it looks like. So you can see there's all this spam happening here, right, in the terminal as we boot up. So the very first thing, all of this gunk, this is just the emulator that I'm running in QueueEMU. It's just telling us that there's been a CPU reset and blah, blah, blah. And then here, the blue stuff is basically, the blue stuff is from the kernel kprintf. So if you call the kprintf function in the kernel, then the first thing it does, it calls color on, and then when it leaves, it calls color off. And this basically just prints out a little escape sequence that makes the output blue if viewed on a terminal. And this is just to help me sort of distinguish that this is a message that comes from kprintf. Anyways, it's not super important, but the very first thing that happens, you can see here, is that it figures out what year, month, and day it is. But instead of looking at these messages, let's look at the code. So the very first thing that happens when I run the run script is what it does, it actually runs a QueueEMU command, and it's this particular one here. And it has all these different settings and stuff. But the important part is that we're using a feature of QueueEMU where you pass in a kernel and a disk image. So QueueEMU has a -kernel option, and basically if your kernel has a so-called multiboot header, which is a boot protocol header that is used by the grub bootloader, then QueueEMU is able to boot that kernel without the presence of a bootloader. And the reason that I use this is because it makes building and running really, really fast, because I don't have to go through the extra step of creating a disk image and installing a bootloader and installing Serenity in that bootloader. Instead, I can just tell QueueEMU to act like a bootloader, and it boots up like really, really fast, right? So boom, and we're up and running. Now, we also have another script here. We have build image QueueEMU, and then we also have build image grub. If you wanted to use the grub bootloader, you can use this to create an image that you can then write onto a physical disk. If you want to boot Serenity on real hardware, for instance, you can use this. And it just helps you get a disk image with grub on it. I mentioned the multiboot header. So multiboot is a protocol that is defined, I think, originally by the grub bootloader. I'm not sure if it's very well supported by other bootloaders, but if we look for multiboot protocol, multiboot specification, yeah, it's a GNU thing, and we're using this version of it, 0.6, and it takes care of a bunch of things for us that we don't have to deal with. And the most important things are we use it to set the screen resolution, and we also use it to figure out what kind of memory the system has, because figuring out what kind of memory a PC has is a tedious task, and the bootloader, this bootloader protocol already knows how to do that. So we just say, hey, if you already figured out what kind of memory there is, why don't you just pass us that information anyway? And then the video mode, actually, let me show you the boot header. So it's in kernel boot, no? Oh, it was moved. It's an Arch i386 boot S. Here it is. And here is the multi-boot header that I was talking about. And basically, or rather, it's down here. These are just macros, more or less, or definitions. So here's the header. And we tell it that we want the memory information and we want it to set the video mode. And this allows us to not have to worry about setting up the graphical video mode. So down here we specify what video mode we want it to boot in, and we're asking for a 32-bit color, and this just makes things easy. Going forward, we're gonna have to implement a bit more stuff like to get better video drivers, but right now I've been using this and it just slaps you into that mode. The big downside of this is that if you want to be in a different mode, you gotta edit these headers. You know, if you want it to be in 1024 by 768, you got to go here and edit this. So this is not super convenient. There are BIOS calls that you can do where you ask the graphics BIOS to set a different VESA mode. But in order to call those BIOS operations, you cannot be in 32-bit protected mode, which the kernel runs in. So you would have to either run in virtual 8086 mode, or you have to switch out the real mode, call the VESA interrupt, and then switch back to protected mode. So that's a big mess, but it's something that is being worked on casually, and we'll see how that goes. Anyways, so this is basically information for the bootloader. So the bootloader will locate this header by like looking through the kernel that we pass it, and it finds these things and it says, oh, you want this video mode, fine. Oh, you want to get the memory info, fine. I will populate, these will get populated with memory information from the bootloader. And then the bootloader will basically send us here. This is where we start execution. So the first thing we do is we just set up the interrupt, and we clear the interrupt and direction flags, and we set up an initial kernel stack, which I think we predefined some space here, 32K here, yeah, just an initial stack. And then we push the multi-boot, the pointer to the multi-boot data structure onto the stack, and that allows us to, wait, why am I doing this way? I'm pushing it, but then also putting it in this. Okay, maybe I don't need to do these actually, but I'm not here to edit code. I'm just here to talk about how it works. So this is the important part. We populate this global pointer, the multi-boot info pointer. We put the multi-boot information in there, and then we call init. And then if init would ever return, we would print a little exit message here, kernel exited, and we would print that and then halt the machine. But we never actually return from init. But init is in C++. So if we go to init cpp, it's this monstrously large function, or file rather. Actually, it's not that monstrous. It's just a couple of hundred lines. Wow. I guess it feels monstrous to me because I don't know why. So here is where we enter into C++ land for the first time. So we go from this boot.s and we jump to init. Itchy nose. And the first thing we do is we check if we have the serial debug command line option set to the kernel, because if so, we want to start streaming all of the kernel output to the serial port. Because obviously, like if you connected a serial port for debugging purposes, you want everything to come on there. You don't want to miss anything. So that's the very first thing we do. And then after that, we call SSE init, which is basically just sets up the CPU so that it allows use of SIMD instructions with the Intel's SSE instructions. And the reason that I do this is because the port of GCC that we build for Serenity, it ends up using SSE instructions. So if we don't do this, then GCC just seg faults. And it would be possible to, you could run Serenity without SSE support if you wanted to, but since every machine that I've tried to use it on so far has had SSE anyway, it just seems silly not to turn it on. And yeah, so after we do that, the second thing is that we initialize kmalloc. And kmalloc is well, it was supposed to be, if you look at the very first comment here, it was supposed to be a really, really, really quick and dirty malloc and free implementation just to get the kernel going. And I wanted to get rid of this and replace it with something nicer before I ever published what I was working on. But then I forgot about that. I forgot about this comment. And then I've just left the comment there because now it's kind of funny. But yeah, so kmalloc is a quick and dirty first fit allocator with a static pre-allocated buffer. It allocates 1 megabyte total of memory, and then it has a bitmap where it's divided into chunks, and each chunk is 8 bytes. And yeah, you can see here it's 1 megabyte, the whole pool. Each chunk is 8 bytes. And then we have the allocation map, which is 1 bit per chunk, and it just tells you if that chunk is used or not used. And then kmalloc will search the alloc map for, like if you want to allocate 32 bytes, for instance, that would be 4 chunks. So then it will search through alloc map, linear scan it until it finds 4 sequential bits that are all zeros. That means that that corresponds to an address where 32 bytes are available. So that's how it works. And yeah, that's basically that. And then, I mean, there's a little more to it than that, and it has a few micro optimizations that make it go a little bit faster than maybe it should. But it's definitely a very crappy allocator, and the size limit is constantly causing trouble because it's very easy to or like get an out of memory panic in the kernel because we exhaust this 1 megabyte of kmalloc memory. Then there's also this concept of kmalloc eternal, which is a separate allocation function. And kmalloc eternal is specifically for allocating memory that you're never going to free. So it is an extremely simple bump pointer allocator that has the next eternal pointer, and it will just, whenever you allocate with kmalloc eternal, it will just give you this pointer and then increment that pointer by the size that you just allocated. And we have a total of 2 megabytes available in the eternal memory space. And I think it starts, no, it comes before the kmalloc range. Anyways, so that's what that's for. So those are the 2 kmalloc allocators. They're the old ones. And then recently I added a new allocator called a slab alligator, which it's used for specific things at specific sizes. So it's an allocator that when you call slab alloc, if your size is one of these, your size has to be less than 48 bytes or less than or equal to 48 bytes, and then we'll find you one of these slabs. So slab allocation is all about having a large cache of same size allocations that you can very easily reuse, because then we don't have to look and find, we don't have to look through like this big bitmap of the available space to see if we can find a fit somewhere, because a slab allocator is essentially just a free list of slabs until you have allocated everything from it. So This is very useful for some of our memory management objects because we allocate a ton of them, especially when you're doing something like running GCC. It ends up very aggressively allocating stuff, and they end up coming out of these, especially Slab Alligator 8. That's the 8 byte per slab. We reserve 384 kilobytes for 8 byte slabs, and it's a very, very busy allocator. And this was just a way to avoid having to go to kmalloc for these things, because this is O of 1 rather than O of n. So it's much, much faster than kmalloc if you know that you need a specific size that we can accommodate. Anyways, after we initialize the two allocators, then the next thing we do is we initialize the ksims, and ksims is the symbols of the kernel, and those are stored in a file. Actually, it's probably something that could be done differently, and I realize now that that was just initializing. We're not loading them. we're gonna load them later. So hold on, we're just clearing out these things. Apparently, I don't know why this is done in a function. I think I probably added this before. This was before startup time constructors were possible in the kernel, and before the kernel BSS was initialized. Actually, startup time constructors are not possible in the kernel yet, but the BSS is initialized as 0. And what that means is that if these are like static file or like globals, basically, and previously these would just have garbage data in them because we didn't zero out the memory segment that contained these things. But now that we do that, it's actually not necessary to have a function that's called on boot that sets these to zeros, although this one is not set to a 0, so maybe there's still some value in having it. But the absolutely right thing to do here is to implement startup time constructors, because then we could, well, this shouldn't actually need construction because this should just be regular data segment stuff. Okay, anyways. This is probably totally unnecessary and could be just, we could just initialize them up there. But that's what it does. It just initializes the stuff related to kernel symbols. We'll get to the kernel symbols in a moment. Okay, and then we create the kparams object, and that's just a convenient object that allows you to check if a particular option is present on the kernel command line. So the kernel command line can contain stuff like serial debug, which will cause us to run, to send all the output to the serial port, and text debug, which will cause us to start the kernel in text mode, and we won't start the Windows server, but instead we'll just start a shell on the console. So this is just for getting to debugging console very quickly. It was added earlier today, actually, by Liev, also known as Supercomputer 7. And anyways, so yeah, that's just what that's for. And then here we just say if this thing is set, it's kind of weird. We should probably just use has. This should be like this instead. Anyway, I'm not going to edit now. Okay, I gotta focus on what I'm trying to do. Okay, so after we've basically parsed the kernel command line, then we will create the VFS. And the VFS is the virtual file system, and it is the it's like the mother object of everything file system related. So the VFS is responsible for the root directory and everything that has to do with files, where you just have a file name and you want to go to, you want to like turn a file name into something tangible, like a file or a device or something. You have to go through the VFS, because the VFS knows which file systems are mounted where. It knows which device numbers correspond to which physical devices, stuff like that. Like the VFS knows all that, so that's what we instantiate here. And then the debug log device, that's just a silly little debug log device. I don't have to talk about that one. And then we instantiate the console, which is a very, very old abstraction that it's very outdated, but it was an early development abstraction where I think I wanted to have some kind of objects that's responsible for receiving kernel messages, so that you could say, now I'm on the virtual console number 1, then it is the console, and kernel output goes there. And if I switch terminals, then the kernel output would go somewhere else, and then you could potentially set it up so the kernel messages go to a log file or whatever. But that's what that was about. And it's still there, and I forgot about it. And then comes a lot of device initialization. So the first thing we do is the real-time clock. And that's actually the first thing that we saw there in the debug output when we boot. It's this right here, what year, month, and day it is. So the very first thing that prints, apparently, prints anything for me, is the RTC, the real-time clock. And it's right here. We compute what time is it now. And then we initialize the programmable interrupt controller. And then we set up a global descriptor table, an interrupt descriptor table. This is just setting up like the x86 CPU stuff, so that like when a certain IRQ or interrupt happens, we have a callback that gets invoked and is able to deal with that. And this just sets up all those mappings and stuff, basically. And then now actually come the devices. So we initialize the keyboard, the PS2 mouse, the Sound Blaster 16, DevNull, very important device, then a bunch of serial ports, and then we make 4 virtual consoles. So you can actually, if you're running in text mode, which, you know, most people never ever run Serenity in text mode, but you can, and you can switch between the consoles with Alt 1, Alt 2, Alt 3, and so on. And it's pretty neat. And then here, of course, we say starting Serenity operating system. After that, we initialize the memory manager. And the memory manager is basically responsible for all of the paging stuff. And it's where you call to when you want to do something like, I need a physical page of memory, or I want to map this virtual memory to this physical memory, stuff like that. The memory manager knows all about that, and when we initialize, actually that's where we take in that memory map that I talked about that we get from the bootloader. So when we call initialize paging, we do a whole bunch of stuff. Like this is where we protect the very first page, so that if you dereference null, then it will actually crash. So important. Because I remember early on, dereferencing null would not crash the kernel or wouldn't crash anything, and it made some things a bit more difficult to debug. It's good if null dereferences crash. But basically here, we will iterate this memory map that we got through the multiboot header, and we will find the contiguous regions of memory and then turn those into metadata for our physical memory allocator. So we create these physical region objects that then they know how much physical memory is available and where is it. And then that's what we use later on if some program or if the kernel wants to allocate like a physical page of memory. Anyways, that's what memory manager initialize is all about. And then it sets up paging and stuff so that virtual memory works. And let's go backwards. Okay. And then we try to initialize the APIC. Now this is very early, like unfinished code, so I just kind of overly eagerly merged a pull request from someone who was working on APIC stuff, because it didn't break anything, and I like where it's going. But it was probably a little too trigger happy on merging it because it was a work in progress. And anyways, it's interesting. So eventually this is basically where we'll go down the path of being able to run multiple CPUs and doing things like SMP. And then here we initialize the timer, the PIT, the programmable interrupt timer. And essentially we're just telling it, hey, give us an interrupt every 1 millisecond. So that's the ticks per second is what we pass to it as the reload value, basically. I mean, we compute the reload value based on this, so we want 1,000 ticks per second, which means that we will get, what is it, IRQ 0? Yeah, IRQ 0, 1,000 times per second, and that's what drives the multitasking in the kernel. So after we initialize the timer, we will walk the entire PCI bus and just dump out all of the devices that we find, because this is just here so that we, early in the boot log, we get like a dump of all the devices, because then we can go and look those up, and if it doesn't boot, then we can figure out, well, okay, so what are the devices here? Like that can usually help you figure out why it wouldn't boot if you're struggling on some new hardware. It's very helpful information. And then here is just setting up the, if it's text mode, then we do nothing, but if we are setting up a graphical mode, then we make a frame buffer device. And this device is what ends up in /dev/fb, which is a device that the Windows server will later memory map and render the screen image into. So if we have information from the multiboot header about a frame buffer, that was the thing I was, or that's something that gets populated if the bootloader is successful in setting a mode, then it will be these values here, and we have the address of the frame buffer in physical memory, so we can just instantiate this thing. So MB VGA device stands for Multiboot VGA device, or I guess Multiboot Video Graphics Array device. But if we don't have multiboot info, we will try to create a BX VGA device, and that's a box emulator card, which is the same card used in the box emulator, VirtualBox, and a QueueEMU. So they're all compatible, and that's the frame buffer driver that we're using here. I think. Yeah, we're using BXVGA. So you can see that we have a frame buffer at this physical address here. Yeah, then after that, we try to set up some network adapters. So we always make a loopback one that's for like localhost communication, talking to yourself. And then we try to detect if there's an E1000, we try to detect if there's an RTL Realtek 8139 compatible card. But auto-detect, these may fail, right? So they only succeed if we actually find a card. So actually, if I run here in QueueEMU, if config will tell us that we only found an E1000 or an E1K. There was no Realtek card. And then after that, we make the procfs, and that's this big class of its own. And then we make a devptsfs as well for pseudo terminals. And devptsfs is kind of interesting. It's oh shit, the mount command. Need to fix this. There's something missing there. But basically, it creates these files in devpts, and this is actually the TTY that I'm on, and it just automatically populates this so that if you have more terminals, like this is now PTS1, then you can see that that file is always there, and it's just a device file that has the correct device major minor number so that you can get to the TTY somehow. This is because when you close this, the sudo terminal goes away. So we don't want the device file to exist after that, and we don't want to hard code them in the dev file system, because then we would have to like decide on a limit on how many sudo terminals there could be. So instead we have a special file system that just generates these files, so you can make as many sudo terminals as you would like in theory. Anyways, and then after we do that, then we initialize the process, which is, now we're getting to the multitasking stuff here. So this basically we make the processes list, which is just a linked list of all the processes in the system. And then I don't know why this is here, but this is just for storing the host name of the machine somewhere. And then we create signal trampolines. And signal trampolines, they're these little pieces of glue code that we use when a signal is dispatched to a process. Then we need a little bit of glue code to like run the signal handler and like return execution back to normal afterwards. And that code is identical in all processes, so we just create it once and then we use it everywhere. And this is where we create that. And then we also initialize thread, which I guess all that does is initialize scheduler. And this is where we create the very first process in the system, which is called the kernel process. And the kernel process is the process that will run when nothing else wants to run. So it's always PID 0, and it only ever runs if there's nothing to do. And it's essentially the idle task of the Serenity kernel. And that's the very first thing that we will do, is create that process. And let's see. So thread initialize actually just calls scheduler initialize, but I'm not going to edit now. And then the first thing we do after this is ready, then now it's time to go to the init stage 2, I call this. I don't know why, but the name stuck. And stage 2 is basically we go into multitasking mode. So we create a new kernel process, which means it's a process that runs with full super user privileges. It can access all memory, everything. And it's just the continuation of this function that we're in, basically. It just jumps to run it in a separate process. And then we also create 2 more kernel processes. We create the syncd, which just, you can see here, it sleeps 1 second and then tries to synchronize any pending writes to disk. I'm not sure if maybe it should sleep a bit longer, but that's what it does. So it's just a process that will wake up every second and see, is there something to write out the disk? If so, I'll just do that. And then we also have finalizer process, which is a very special process that when a thread or process dies in the system, then it doesn't run its own destructors and it doesn't do its own teardown. Instead, it just goes into a zombie state, and then the finalizer kernel task, when it gets to run, it will go and run all the destructors and do all the teardown on the behalf of the dead processes. So this is just a way to have like a clean room environment when you are tearing down a dead process, because you don't want to be like in a potentially weird context when you want to do teardown. So we just let the finalizer do that. Originally, I was doing teardown in the scheduler code, but I found that it was much nicer to keep the scheduler very simple and not do stuff like process teardown in there, and to just put that in a separate task. So after we create these 3 initial things, then we call scheduler pick next, and we enable interrupts, and then we go into the idle loop. So pick next, that just means pick the next thread that should run, and then we set interrupts enable, which means that the timer interrupt will come very soon, within 1 millisecond, and do a task switch. And then the idle loop, that's just this. We just call halt in a loop, basically, with a little optimization to reduce latency, but it's not terribly important. But then I guess we could look at the second stage of init. So init stage 2, it's just basically just continues initializing more devices. And actually we initialize the system call interface. So system calls in Serenity go through int82 hex. And there's, if you look in syscall.h, there's a huge list of different syscalls that you can make. All of these, you do them through the int82 interface. And in assembly, the syscall looks like this. So it's int82, and then you pass the argument, the function number in AX, and then the arguments, up to 3 arguments in DX, CX, and BX, respectively. And if you want to pass more information than that, then you have to pass them as a pointer to a struct. And here are some examples of that, like the select syscall, for instance, has more than 3 arguments, so we pass them in a struct instead of passing them directly. Yeah, and then in its stage 2, we just initialize more devices like dev0, dev full, dev random, the PTY multiplexer, and then we figure out what's the root device that we should mount the file system on. Like what file system should be mounted on slash, and we get that from a kernel command line parameter. So I think we're not using a command line at all here. I'm supposed to say append. Yeah, this is the command line we send, actually. We say hello on the command line. So it just defaults to dev HDA. And then there's a bunch of code here that looks through, it takes the string and then looks at the different partition tables and tries to figure out, well, what's the actual root device that you want. And once it has some idea of what device you really want, then we see if we can find an ext2 file system on it. And if that doesn't work, then we just hang the machine, because right now we have to have an ext2 root file system. And if we manage to instantiate an ext2fs object, then we say vfs mount root with this file system. And this, after this point, the root directory is this file system right here. And it's not possible to unmount root. It will stay forever. And then here actually is finally where we load the ksims. So that's the kernel map, and we find that by asking the VFS to open the /kernel map file. And the kernel map is produced by the build here, and it's just a sorted list of all the symbols in the kernel with their C++ names demangled. And this allows us to do backtraces. So you can see, like if we exit a process, then you can see here, like what was the stack trace. And everything that happens in the kernel, like right here, these are kernel stack frames, they come from the kernel.map. And we load that whole thing on startup and store all of the kernel symbols in a big table so that we can look them up quickly for generating these stack traces. It's very handy to have proper named stack traces like this. Very helpful for debugging. And then here is Jesse's code for for the floppy disk drivers. And I've never actually tested this with a real floppy drive, but I hope he has. I hope you've tested it on a real thing, Jesse. Sometimes I wonder why we have floppy support, but it is cute. We'll see. We'll see what happens with that code. I don't mind having hardware support as long as someone is using it. It's totally fine, but if no one is using it, then I'm a little bit skeptical. Anyways, and then here is where so if we're booting in text mode, like I mentioned earlier, then we will just create a shell. But if we're booting in outside of text mode, so regular graphical mode, then we boot this program called the system server, and we say that the first terminal is graphical. That just means that basically what that means is that we will let the Windows server deal with incoming keyboard and mouse events and stuff like that, and we don't try to hog them and act like there's a text console. So at this point we just launched the system server, and we also launched this other thing called the network task. And the network task is a kernel task that is responsible for incoming network packets. And that's this whole thing of its own. But basically it's a kernel process that runs a loop that just waits for incoming packets from the network and then processes them and puts them in the right queues and stuff so that they can be picked up by the different other networking code in the kernel. Because it's sending something out to network, you can just do that when you want to send, usually. But when it comes to receiving, it's nice to have all that in a single place. So that's what we do there. We just have a separate task for that. But ultimately, though, like we should probably let the network task do more sending and retrying and stuff like that. It's not super sophisticated yet. It needs work. A lot of these things need work. And then after we launch network task, we call exit, because this exits the init stage 2 process because it's now done. And it has left system server running instead. And if we look in the system server program, now this is a regular user space program. It's in bin system server, and it's sort of like the init program. And the first thing we'll do is just run mount-a, which will go through the etc, what is it, fs tab, find it and finds these, and they will mount these file systems one by one according to this file. So just make sure that proc file system is mounted on /proc. We have wpts where it's appropriate, and we actually have a tempfs in /temp. Tempfs is a special file system that does not write temporary files out to disk. Instead, we just allocate memory for each file and store it in memory. So it's like a RAM disk. And then after we mount everything, we start a single text console just in case you would need it. And then we start up the lookup server, which is the DNS resolution server, and the Windows server, the audio server for sound. We start the taskbar, which is still a little thing on the bottom here. This is the taskbar. We start this first terminal and this launcher. And then we go into basically an infinite loop where we sleep a lot. So this is just so that system server doesn't go away. And that's it. That brings us to the state that we are in now. We have booted up, these programs have been started, and we are ready to use the system. And yeah, I guess that's that. That's how we boot. I hope I managed to cover most of the important parts. Obviously, if you have questions, you're more than welcome to ask, but I definitely encourage everyone who's interested in this to look at the code, mess with it, play with it, take a deep dive in any part that you're interested in. I'm happy to answer questions about that. I'm happy to discuss how it works, how it should maybe work, and stuff like that. If you want to talk in depth, you can find me on IRC, in the Serenity OS channel on Freenode. But GitHub issues, all those things, you can always communicate that way too. But yeah, so since a lot of people asked about this, I hope that you found this informative. I realized I was probably going pretty fast, but I just wanted to cover as much as possible and get all the way from from boot to here. So yeah, if you made it this far, then I thank you for watching, and I really hope that you saw something interesting here. And yeah, thank you for checking it out, and I will see you next time. Happy hacking.